Okay, in exercises 75 through 80, we have the second part, or what our book calls the second fundamental theorem of calculus. So let's review very quickly what we're talking about here. The first fundamental theorem of calculus, according to our book, says that the area under the curve of a function between two x values is equal to the antiderivative evaluated at the upper limit minus the antiderivative evaluated at the lower limit. Sometimes we write that with the integrand being a derivative, which we really want to think of that the integral as an antiderivative. So if we treat the function there as a derivative, then the definite integral from a to b would just be the antiderivative evaluated at the upper limit, antiderivative minus antiderivative evaluated at the lower limit. All right, so that's the first fundamental theorem of calculus, or the first part of the fundamental theorem of calculus. The second part is stated in this way. It says that the derivative of an integral defined function. Now, it doesn't matter what the lower limit of integration is. The upper limit is a variable this time. It's x. It's not a constant. It's a changing quantity. And this time, instead of writing f as a function of x, we're going to write f as a function of t, just so that there's no confusion here. I call this an integral defined function. What's there inside the brackets is really a function. When I change the value of x, I'm going to get a different area under the curve. When x is one value, I have a certain area. When x changes to another value, I have a different area under the curve. So for every value of x, there's a different area between the curve and the x-axis. And so I call that an integral defined function. And since it's a function, we can find its rate of change, or its derivative. And the second fundamental theorem of calculus very simply says that the derivative of the integral defined function is the original function. Now, let's take a look at what that might mean here. So we're going to start off with number 75. And 75 says capital F of x is this integral defined function from 0 to x of t plus 2 dt. And so what we're going to do here is just treat this the way we have treated each of the definite integrals that we've worked with so far. And that is, we want to find the antiderivative of t, so that would be t squared over 2. And the antiderivative of 2 would be 2t, and we're going to evaluate that from 0 to x. And I'm just going to move those over. I think we can finish this all on one line here. And so we want to evaluate that antiderivative at the upper limit. That's x squared over 2 plus 2x. And then when we plug in 0, we're going to get 0 on the other side. So that's really that is the function f of x. Now, what the instructions say are integrate to find f as a function of x. That's what we've done. Then demonstrate the second fundamental theorem of calculus by differentiating the result found in part A. So now what we're going to do is take the derivative of what we just found with respect to x. And we bring down the 2, the 2's are going to cancel, and we end up with x plus 2. So what have we shown here? Well, if you look at the integrand that we were working with, well, that was just t plus 2. So how do we find the derivative of this integral defined function? All we did was plug in x for t, and we're done. So the rule said that the derivative of the integral defined function from some constant to x is just f of x. And so that's what we can see here with the x plus 2. All right, let's go on to another example, number 75. All right, 77 rather. All right, with 77, I have f of x equals the integral from 0 to x, and I've simply rewritten cube root of t as t to the 1/3 power. So we're going to find the antiderivative of t to the 1/3. That becomes t to the 4/3 divided by 4/3 or multiplied by 3/4. And that's it. And we're going to evaluate this at x minus evaluate at 0. So we end up with 3/4 x to the 4/3 and then plugging in 0. And so that's it. Now, what we want to do is we want to take the derivative of that. So we'll say f prime of x, that's just the derivative of what we just found. And when we bring down the 4/3 is going to multiply times 3/4. They're reciprocals, so that product is going to be 1. And we reduce the exponent from 4/3, we reduce by 1, and we end up with x to the 1/3, which is essentially what we had as the integrand previously. All right, let's do number 79. And hopefully, although you may not understand exactly what the point here is, we're going to see in the next set of examples that doing these problems is pretty straightforward. All right, so we're starting with integral from pi over 4. This time our lower limit of integration is not 0 anymore, and we have secant square of t dt. All right, so we want to find the antiderivative of secant squared, and that's just tangent. Tan t from pi over 4 to x, and we plug in the x and we get tangent of x, then tangent of pi over 4 is 1. Now we're going to see why it doesn't matter what that lower limit of integration is, because when we take the derivative here, the derivative of tangent of x minus 1 is derivative of tangent is secant square of x, and the derivative of 1 is 0, so we end up with secant square of x, which is essentially again the integrand that we had in each of these cases here. All right, so this is we're going to stop this video at this point here, but this is an example then of what we're trying to work with the second fundamental theorem of calculus. And its importance is that without the second fundamental theorem of calculus, which really doesn't have a whole lot of usefulness, we can't prove the first fundamental theorem of calculus, which is extremely useful, and it is one of the most useful formulas in all of calculus. All right, so we're going to stop this video at this point.